I am Masato Takei. I'd like to thank the organizers for giving me 3 talk slots. Today, I'd like to talk about, discuss limiting behavior of 2 repelling random walks on one-dimensional lattice. This is, my talk is based on joint work with Sam Suzuki, who is my former graduate student in Yokohama National University. Last week, I gave 2 lectures on elephant random walk, and although elephant is not in my title, this model is somewhat related to elephant random. No. So let me begin with the usual elephant random walk. The elephant remember all of its previous steps, and it remembers one of them, a uniform probability, and in the next step, it takes the same step with probability P, or taking the opposite step with probability 1 minus. This is the standard setting produced by Switch and Team. Today, I'd like to discuss some interacting random walks. And this is the one generalization of one generalization. 2 elephant random walks with coupled memory. There are 2 elephants, red one and blue one. And for the first elephant, with probability gamma 1, it remembers its own history and taking a similar dynamic. And with remaining probability, thank you. With remaining probability, elephant 1 uses the memory of the second, and the remaining dynamic is similar. This kind of elephant random model was introduced by Marchioni in 2019. To my best knowledge, he first introduced such a model. And in his paper, he obtained recursion formula for the moment, first, second, and more. And in the later section, he did further analysis of so-called what he called cow and ox model. This is a bit confusing. In this setting, elephant 1 is cow, and it is the standard elephant, which means the elephant 1 can use its own memory. And only the elephant 2, in this case it is ox, can look at the memory of cow. And this model has its origin in another paper by Mora and others. And their motivation is to have a model to quantify OT. And by Marchioni's analysis, this cow and ox model has 2 prominent behaviors. One is one animal chases the other, and in the second situation, they separate from each other. Now, the model which I like to talk about is similar feature, like in the second stage. my talk is concerning an open problem about the recurrence or transience of two repelling random walks introduced by Prado, Poetti, and Rosales. And I forgot to translate this Chinese character, but you can easily guess. This zone in there. This is convenient because this is too short. I think you understand it. Now, let me explain the informal description of this work, quoted from the abstract in this those page, earlier page. This is two random walks on the integer lattice, and the transition probability of one walk in one direction, like left, decreases exponentially with the number of transitions of the other walk in that direction. Then the joint process may be seen as two random walks being forced to repel each other. And the strength of the repulsion is modulated by a single parameter beta. And in their setting, beta 0 corresponds to two independent symmetric random walks. And the main result in Prado and others is as follows. There are two different positive finite values such that both random walks are recurrent with probability 1 if beta less or equal beta 1. Beta 0 case, they are usual symmetric random walk. So each walk will visits every point infinitely off. And similar behavior appears if beta is small. On the other hand, beta is larger than beta 2, then each walk will transcend, and actually both go to infinity. One goes to plus infinity, and the other minus infinity. As I mentioned, as I said earlier, in this paper, they doesn't mention elephant random walk at all, but from this informal description of the transition, you may feel this process is quite similar to coupled elephant random. And actually, by our analysis, this is indeed quite similar to elephant random walks in some region of data. I will skip this formal description of the model. I put it just for your reference. And the feature of this random walk is the phase transition at the special value T3/4. It becomes super diffusing when T exceeds 3/4. That to explain our interacting random walk model, let me reduce some of some of known results for the standard. And to understand the behavior of this random walk model, it is convenient to introduce a new parameter alpha defined by 2p minus 1. This parameter describes the effect of step reinforcement. If p exceeds half, then the elephant prefers to stick to the remembered step. And if p is half, then it is just a symmetric random. And if p less than half and alpha negative, then and the elephant prefers the opposite of the Rickenberg state. To state further properties of this random walk, it is convenient to use this imperfect alpha. For example, the expectation of the position is like this. This is the expectation of the first step, and its effect is enlarged or shrunk by this factor, n to the power alpha. And so if alpha exceeds half, then it is dominant compared with the usual fluctuation. And actually, looking at the second moment, there is a phase transition at alpha half. This corresponds to P 3/4. Now I'd like to explain limit theorems for this standard model. First slide is about the subcritical regime of P less than 3/4. In this regime, the elephant random walk is quite similar to the symmetric random walk. And in this central limit theorem, the scaling factor is usually square root of n. But in the limiting variance is larger than 1 if alpha is positive, and less than 1 if alpha is negative. And corresponding low iterative logarithm is also obtained. And in particular, this LIL implies almost a recurrence of the elephant. And the second result is about scaling. Using the diffusive scaling, we obtain this diffusion process, recently described by this stochastic integration. And it is nothing but time change process, time change version of Brownian motion. And such kind of diffusion process is often appears in this kind of random. Now, this class of diffusion process is called the noise reinforced Brownian motions. This functional CLP is first obtained by Bauer and Beltran by using a connection to Fourier and Spin. And later, Beltran derived this kind of diffusion process from a broader class of step-reinforced random. In that paper, he named this process a noise reinforced Brownian. LI is obtained by Coretti. And this limiting process will appear in the repelling random walk, which I like to talk about. Next slide is about the critical regime and supercritical. In the critical regime, this variance diverges. So if we put log n here, then we can recover the standard normal distribution. And we put log n here and here, then the law of iterative logarithm will continue to hold. And in particular, this implies, again, almost sure recurrence of the elephant. And if P exceeds 3/4 or alpha exceeds half, then the situation will change. And now we need recurrent scaling n to the power alpha. And by this scaling, we obtain a limit. And this convergence is almost sure and in LP sense. And the limiting behavior is an absolutely continuous random variable, but non-Gaussian. This statement was proved in series of papers by different authors, but in particular, L don't have a point mass at 0, so this implies almost sure transience the elephant. Also, this limit variable is non-Gaussian. If we subtract this random drift generated by the memory effect, then by diffusive scaling, we can obtain the standard, the Gaussian distribution, and this kind of LIL still holds. Up to now, I reviewed the standard result for standard elephant random walk. Now, several variations of elephant random walk have been studied. The first one is the multi-dimensional case, and the second one is the elephant random walk with non-uniform memory. In the last week, we explained this results for such a model. And the third generalization is the step size distribution. This is called step limitless random walk with more general increment than plus minus 1. This was first studied by Bizinga with heavy tailed increment. In her case, this is called sharp random swing network, and further studied by them. And many other variations. Today we focus on interacting elephant random. And there are a few papers on this subject up to now, but one of the earlier papers is Athreya and Rajat. This is a simulation study of interacting elephant random walk, which is quite similar to exclusion test. This is simulation study, and in the next slide, I will explain mathematical studies in this subject. The title is Interacting Elephant Random Walk, but this contains zero interaction with zero interaction page. I will explain some result on this case also in the next subsection. And this is introduced in the very first part, and two elephant random walk shared memory. This is a special case of Marchioni, and recently there are two papers. One is by Evolutionist, is there, and the other is Agechi and Kim. In this model, at time n+1, elephant 1 looks at the past n of elephant 2. So just to use the memory of the other elephant and select one of them. And further dynamics is okay. And parameter can be depend on the number of the elephant. And two repelling random walks I discussed informally turns out to be similar to this kind of model. And actually, in the Devonsh's paper, we develop a quite general theory for multiple elephant random walk with graph-based shared memory. In this talk, we focus on two elephants. And before going to repelling random walk, I'd like to explain two independent random walks. This has some historical background. In the Pearson's paper, the term random walk first appeared. And 10 or something after 20 years, Korea started the famous study of random walk on the D-dimensional lattice, very famous work. His main motivation was to find the probability of that two independent random walk eventually make each. Generally, what is the probability of returning to the home after drinking or something? But actually, his motivation was like that. So our question is, how often can two independent elephant random walks? And the result is as follows. This is by Matthew, myself, and Hideki. Let those processes be independent elephant random walk with the same memory parameter. Then, if less or equal to 3/4, then they can meet infinitely many of. On the other hand, if we exceed 3/4, then they can meet only finitely many of. So if memory parameter is large, then they eventually won't meet each other. The proof of this theorem is quite short, and there is some common feature with our analysis of two repelling random. So I will talk about the proof. Please notice that the difference of two elephants is no longer elephant. But if P is less or equal to 3/4, then elephant random walk process can be approximated by noise reinforced Brownian motion with probability 1, and with this this small remaining data. So the difference of the elephant random walk is difference of noise reinforced Brownian motion, and this difference is right. By some calculation, this can be expressed by time change processes of Brownian motion. D and D prime are independent, and this depending on if P is 3/4, then a log time change appears. Because D and D prime are independent, this has the same distribution as a single Brownian motion, and applying log iterative logarithm for the standard Brownian motion, then we obtain this oscillatory behavior of the difference. This implies the infinitely many collisions of two elephant random. This is the small p case, and for large p case, in this case, both of elephant has super linear behavior, super diffusive behavior, and let us look at the coefficient of this this term. The L and L prime are random variables, and those are independent, and both of them have continuous distribution. This was proved by previous study by other groups. So the difference is like this, and this coefficient cannot be zero with probability. So two independent random walk cannot meet infinitely many walks. In our paper, the memory parameters of two elephants are exactly the same. And there is a generalization done by Shibata and Shirai. In their paper, two different parameters is weekly. And their result is like this. P and both P and P prime less or equal to 3/4, then they can meet each other infinitely. Otherwise, they meet each other only finite. The basic idea of the proof is quite similar, but in this case, the approximate process is no longer Brownian motion, but it is a centered continuous self-similar Gaussian process with very good decay, very good time correlation decay. So in their paper, very handy LIL for such processes. Their LIL will be useful for other applications. This is about the independent elephant random. I have 10 minutes. Yeah. Finally, we reached the model in our title, to repelling random. In their model, they use this kind of exponential function, and this data is called the strength of repulsion. I put picture here, and two random walks. The dynamics of two random walks are defined as follows. For simplicity, we assume both random walks start at origin. And the conditional distribution of the increment is given by the product of P1KU, P2KU. This PIKW is defined by this function. The 3 minus I is the stand for the other elephant, and W, if W is +1, then this function becomes like this. So if the proportion of the pluses the number of pluses are dominant, then the other elephant takes the step to the opposite, minus negative division. And actually, in their original setting is more complicated. We can generalize first K0 step. We can give arbitrary steps, and then with slight modification of the transition function, we define the model and similarly. And all the results given below holds true in this general setting. So this simpler setting will help you to understand the situation. This is a summary of results obtained in CAD and others. If data is zero, then two random walks are independent usual random. So each process is recurrent, and the CLT, LI, and everything are obtained. And for data positive but less or equal 1, then this strong law holds, and each process is recurrent with probability. And between 1 and 2, just this strong law holds. And if data exceeds 2, then situation changes. And in this case, the strong law takes a different form. The limit is W or minus W, and this W is given as a unique solution of this equation. And anyway, W is strictly between 0 and 1. So in this case, the walker is transient with non-random positives. And one goes to plus infinity, and the other goes to minus. The main problem in their paper is recurrent or transient processes. So in the intermediate regime, such a result is not known. And to compare with our result, we rewrite this result in a different form. The limit is random, but this random limit this random limit has two possible values, W or minus W. And this is a quote from Brad's paper. The recurrence ranges of both random walks remains widely open when data is between 1 and 1. This is an overview of our result. This is going to appreciate. And first, we obtain CLT and LI missing in this regime. How about the intermediate regime? For this case, we obtain such a result. If data is strictly between 1 and 2, then we obtain similar, we can prove transience for the process. But in this case, the speed of transience is slow, and this is n to the power beta by 2, and the limit has positive variance, and it is not 0, this probability. So, in the previous study, this region is widely open. Now the situation is 1 point remains. I'd like to explain some reason for this in the last slide. Now explain the more precise statement of the result. And the theorem 1 is for the subcritical case, data less than 1. In this case, this joint CLT holds, and correlation coefficient in the limit is exactly minus beta. This is between -1 to 0. And corresponding LIL holds, and this implies almost sure recurrence. In the previous paper, Prado and others proved recurrence by delicate comparison with independent random walk with inhomogeneous transitions. But by proving this limit theorem, we can obtain the recurrence as a corollary. And in this regime, we can obtain the scaling limit. And this limit is looks complicated, but sum of two independent noisy reinforced Brownian motions. One is with parameter minus beta by 2, and the other is with parameter beta by 2. And in the simplest initial condition, those two processes has the same distribution. But in general, we don't know. Okay. The limit is anyway the same. In the critical regime, we have a similar CLT and LI, but with with additional logarithm. And in the for the scaling limit, we do not obtain Brownian motion, but this kind of scaling limit. It is the standard normal variable, and just multiplying the square root of it. It just this is the scaling limit for the critical. This and here is the result for the intermediate regime between two critical points. In this regime, only this was known, but we obtain the precise order. We found precise scaling for this case, and the limit variable has a continuous distribution, no point mass, and so we obtain the transience of this. Transience of the elephant that walkers in this region. Comparing with our theorem, if data is larger than 2, we have the random limit also, but the limiting variable has a discrete distribution. This is a difference between those two cases. Anyway, the data 2 is the second critical point. Where it has transition from zero speed transient to positive speed transient. Now almost time is over, but our result for data less than 2 are obtained by several techniques developed for elephant transient and other related models. And actually, key point is to prove some or different process can be approximated by elephant random walks with suitable parameters. And there is some open problems outside elephant random walk like this. The prominent one is to show zero speed transients at the second critical point. In this case, everything is degenerate, and we have been unable to obtain any result and something more. Okay. Thank you for your attention.